Hello, my dear students and friends. This is Rami Khan. Today, in this video, I am going to cover about ethers, their IUPAC nomenclature, their preparation, and their chemical properties. So, without wasting any time, let us start. So, let me off image. Okay, let us start. First of all, what are ethers? Okay, ethers are those organic compounds having this formula, this R O R. So these two R can be same or different. If they are same, then they are called symmetrical ethers, and if they are different, then they are called unsymmetrical ethers. Okay, so here are examples of ethers which include symmetrical and unsymmetrical ethers. The first uh, example is dimethyl ether. This is dimethyl ether in which the two alkyl groups are different, are same. Sorry, they are same. Okay, so here in this example, the alkyl groups are different. Here it is methyl and this is ethyl. Okay, so this is an unsymmetrical ether. So in IUPAC nomenclature, ethers are named as alkoxyalkane. Okay, in alkoxy part we have this smaller number of carbon atoms with O. This part is alkoxy part, this part is alkoxy part. So this R must contain lesser number of carbon atoms than the carbon atoms present in this R. Okay, so in the alkane part we have larger number of carbon atoms. So for example, the first example is this dimethyl ether. Common name is dimethyl ether. So we must take this part as the alkoxy part, and this part is our alkane part. So this is called methoxymethane. Methoxy, CH3O is called methoxy, and the CH3 will be our chain. So methoxymethane. Okay, and here in this case, this is, let me write over here. This is CH3O CH2 CH3. So this part has lesser number of carbon atoms and here larger number of carbon atoms. So this part must be included with O in IUPAC nomenclature. So this has to be called methoxy, and the chain of this carbon contains how many carbon atoms? 2. So this has to be named as methoxyethane, right? This is methoxyethane. So in the third example, I have taken this one, CH3 CH2 CH CH3, and to this OCH3 is attached. So we must choose a chain which contains larger number of carbon atoms. So this carbon atom has to be numbered as 1, 2, 3, and this is 4. And the methoxy OCH3 is attached to the second carbon atom. So the name, IUPAC name of this compound is 2-methoxybutane, since the carbon chain has 4 carbon atoms. Okay. Now next example is OCH3 is attached to benzene. So benzene has to be our chain and methoxy has to be the side chain. So methoxybenzene is the IUPAC nomenclature of this compound. This is an unsymmetrical ether. Its IUPAC nomenclature is also anisole, which is also its common name, right? I'm taking another example here, over here. So this is a cyclic chain to which OCH3 is attached. This is OCH3 and this is OH and this is Br. Among these functional groups, OH is our principal functional group. This is our principal functional group. So the carbon atom to which OH is attached has to be numbered as 1, right? So this is 2, this is 3, this is 4, this is 5. So bromine is attached to the fourth carbon atom, so 4-bromo. And the methoxy is attached to the second carbon atom, 2-methoxy. 4-bromo, 4-bromo, 2-methoxy. This is our prefix part. Cyclo, because the chain is cyclic in nature, so we have to add cyclo, which is our primary prefix. This part is our secondary prefix. And the word root, since the chain has 5 carbon atoms, so we have the word root pent, and in is double bond is present in the second carbon atom, so 2 in, and removing E because the secondary suffix is ol, starts with O, so we have to remove E of ENE and the 1 ol. This is the IUPAC nomenclature. Okay, the last one in the list is two benzenes are attached to oxygen. This is our oxygen, this is our ether. So one has to be taken as the prefix phenoxy. This is called phenoxy, and benzene, phenoxybenzene is the IUPAC nomenclature of this compound. Okay, these are some IUPAC nomenclatures. So let us move to the next topic, which is the preparation of ether. Okay, the second one is preparation of ether. So we have two reactions in the preparation of ether. The first one is from alcohol by dehydration. So when alcohol is reacted with concentrated H2SO4 at a temperature of 413 Kelvin, then we have we have ether as the product along with water. So this is dehydration, water is removed. So I can simplify this reaction like this. This is an ether, this is an alcohol, and we must take another alcohol, this. So when concentrated H2SO4 is added, which is a very good dehydrating agent, so it removes one hydrogen from one alcohol and OH from another alcohol. So after removing out this water molecule, we will have this ROR. This is our ether. Okay, I am giving two examples here. CH3 CH2OH, this is our ethanol when this is reacted with concentrated H2SO4 at 413 Kelvin. Then ethoxyethane is formed. This is called ethoxyethane. In common name, this is called diethyl ether. Okay, so ethoxyethane is formed. Temperature, remember, temperature has to be 413 Kelvin. And if this same ethanol is reacted with concentrated H2SO4 at a higher temperature, that is 443 Kelvin, then elimination reaction takes place to form alkene as the product. Okay, this is also dehydration of alcohol. This is also dehydration of alcohol. This is substitution reaction, SN reaction, you can say, and this is elimination reaction. Okay, at higher temperature, elimination reaction takes place, removing water. At lower temperature, 413 Kelvin, substitution reaction takes place to form ether. Okay, giving another example here, methanol is reacted with concentrated H2SO4 at 413 Kelvin, then methoxymethane is formed as the product, okay, along with water. So these are the preparation of ethers from what? Alcohol by dehydration. Another example for the dehydration of for the preparation of alcohol ether is from alkyl halide by Williamson synthesis. Okay, this is our Williamson synthesis. This is very important for examination. It is frequently asked in your council or board exam. So when this alkyl halide, any alkyl halide, this has to be X has to be chlorine, bromine, or iodine, not fluorine. Alkyl fluoride is very less reactive. When this reacted with RONA, sodium alkoxide, okay, sodium alkoxide, when it is reacted with sodium alkoxide, this has to be plus and this has to be minus. This is our alkoxy group, which acts as nucleophile to attack this alkyl group to displace this halogen, so to form ROR, ether as the product along with NaX. Okay, so this is SN reaction actually, and the reaction can be SN1 or SN2. Usually this is SN2 reaction, but it can be SN1 also. It is SN2 reaction, okay, not SN1. And now let us take some examples for this reaction, for this Williamson synthesis. The first reaction is methyl chloride is reacted with sodium methoxide. Then what would be the product? This is the question. Okay, so let me write the product here. This methyl chloride is reacted with sodium methoxide. This methoxide ion acts as nucleophile to attack this methyl to displace this Cl. So we will have this product. Let me write over here CH3OCH3. This will be the product for the first example along with sodium chloride. I am not writing sodium chloride here. In the second example, ethyl bromide is reacted with sodium tertiary butoxide. Okay, sodium tertiary butoxide. So here the product would be, let me write the product of this reaction here. So this will be CH3 CH2 to this CH2, this O will be attached to which three different alkyl groups, methyl groups are attached. So this is an ether having a tertiary. I'm sorry, this is not the product. Yes, this is not the product. Okay, this is wrong. This has to be like this. To this O, carbon has to be attached, and to this carbon, three methyl groups are to be attached like this. This has to be the ether. Okay, so to this ether we have a tertiary alkyl group attached. Okay, so the name of this ether will be, this is our first carbon atom, this is second carbon atom, this is third carbon atom, this is the chain, and the ethoxy group as a side chain and methyl as a side chain. So the name of this compound, IUPAC name of this compound is 2-ethoxy, then 2-methyl, because methyl is also attached to the second carbon atom, 2-ethoxy, 2-methyl, then propane is the IUPAC nomenclature of this ether, right? So this is the product along with sodium bromide. Okay, let us move to the third example. In the third example, this is a different reaction because we are taking a tertiary alkyl halide. Now here the point is, when a tertiary alkyl halide is taken, then the product would be different. Okay, so let me write the reaction here. Let me show here. The reaction occurs like this. When a tertiary, this is methyl. Okay, I'm writing hydrogen separately. When this is reacted with what? CH3ONa, in which this methoxide ion will act as a base to abstract this hydrogen from beta carbon atom. This is a beta, this is alpha, this is beta. So beta hydrogen is abstracted by methoxide ion as base, and these two electrons will form a pi bond over here, and this cell will move out. So we will get CH3C double bond CH2CH3 as the major product. This is an alkene, and along with this alkene, methanol, because CH3O minus abstracts this hydrogen, so we will have methanol as one of the byproducts also, plus NaCl. So this alkene will be our major product for this particular reaction. Okay, this is the product here. Okay, now let us move to the next reaction. This is the reaction. Let me write here. This is our methyl chloride, and this is reacted with sodium phenoxide. So phenoxide ion is a good nucleophile, so this attacks this carbon atom and displaces this hydrogen. So we will have this as the product. To this methyl, oxygen will be attached, and to this oxygen, benzene will be attached like this. So this is our Ne-sol. So the product of this reaction, the fourth reaction, is here, phenoxide. This is our Ne-sol, methoxybenzene, right? In this next reaction, let me write here, this is our chlorobenzene. This is our chlorobenzene, and it is reacted with sodium methoxide. So methoxide is a nucleophile, and this benzene has excess of electrons, so it cannot easily attack this benzene ring as nucleophile. In fact, in benzene and derivatives of benzene, SN reaction is very difficult to occur. So normally no reaction takes place in this case, because it needs to be heated. The reaction mixture has to be heated at a very high temperature so that the reaction occurs. Okay, normally the reaction does not take place at this stage, at this condition. Okay, so these are the preparation of ether. Let me move to the next topic, which are the chemical reactions of ether. So In chemical reactions of ether, we have two types of reaction. The first one is nucleophilic substitution reaction, and the second one will be electrophilic substitution reaction. So the first type is nucleophilic substitution reaction, in which ether is reacted with hydrogen halide. This X can be chlorine, bromine, or iodine. Okay, so the reaction goes like this. This is our alkyl group, oxygen, and this is another alkyl group, and if it is reacted with HX, this is HX, X minus can attack this carbon atom to which oxygen is attached in either SN1 way or SN2 way. Okay, SN2 or SN1 way. So generally SN2 reaction takes place. To form, this bond will be broken to form alkyl halide. This is our alkyl halide, and this will be our alcohol, because to this RO hydrogen will be attached. Okay, so alkyl halide and alcohol will be formed as the products. Okay, and the reaction follows SN1 or SN2 mechanism. Okay, so this is the first example, methoxymethane, in which HCl is reacted with this compound, and since this ether is symmetrical in nature, either this bond or this bond can be broken. Whatever you like, you can break any bond. So we will get CH3O, CH3OH methanol, plus to this CH3 halogen will be attached CH3Cl, because this chlorine will attack this carbon atom to break this bond. Okay, this is our CH3. Okay, now in the second reaction I am taking an unsymmetrical ether, which is methoxyethane, and it is reacted with HBr. Again SN2 mechanism will follow, so Br minus will attack as nucleophile to this carbon atom having less steric hindrance, because attacking this carbon atom by Br will have some steric hindrance by this methyl group. So attacking this carbon atom would be easier. So this Br as our nucleophile will attack this carbon atom. So let me write over here CH3 CH2O CH3, and if it is reacted with HBr, so our Br minus will attack this carbon atom as nucleophile, and this bond will be broken. So we will get CH3 CH2O. To this O, hydrogen will be attached, so ethanol will be formed, and to this methyl bromine will be attached, so methyl bromide will be formed. So these two will be the products. Okay, in the third example I am taking a symmetrical ether, ethoxyethane, okay, diethyl ether, and it is reacted with HI. This is HI, and very important here, it is written that excess. Okay, let me write the reaction here. This is CH2 CH3 CH2O CH2 CH3, and it is reacted with HI and excess. HI is taken in excess. Okay, the reaction follows SN2 here also. Iodide ion attacks this carbon atom. Iodine will attack this carbon atom. This oxygen carbon bond will be broken. This is to be broken. So we will have ethyl iodide and ethanol as the product. This is our ethyl iodide. Now another product will be our this ethanol. Let me write here ethanol. This would be the product, but since HI is taken as in excess, so iodide ion will attack this carbon atom to displace this hydrogen again to form ethyl iodide again. So we will have 2 moles of ethyl iodide as the product. In this case, no alcohol will be formed. Remember, 2 moles of ethyl iodide will be formed. Okay. In the third example, iodide ion attacks either this carbon atom or this carbon atom. So since this is a tertiary alkyl group, let me write here after removing this. Okay. Okay, so let me write here, this is a tertiary alkyl group, and if a tertiary alkyl group is attached to oxygen in an ether, then reaction undergoes SN1 mechanism, not SN2. So before attacking by the nucleophile, this is HI, okay. So before attacking by iodide ion, this bond will be broken to form a stable carbocation. So we will have this as the intermediate. This carbon will have a positive charge. To this positive charge, iodide ion will attack to form this tertiary haloalkane, and to this O hydrogen will be attached. So this would be our products. A tertiary haloalkane and a methanol will be formed as the product in this case. Okay, these are the product for this reaction. And for this is anisole methoxybenzene, and if it is reacted with HBr, then since resonance can take place here, this carbon oxygen bond has partial double bond character, so this bond is not broken. So this bond has to be broken. So bromine has to attack this carbon atom to form ethyl bromide, right? And one other product will be our phenol plus methyl bromide will be the products. Okay, these are some examples of SN reaction of ethers. Let us move to the next type of chemical reaction, which is electrophilic substitution reaction. So this is the second and the last type of chemical reaction of ether, which is in your NCERT syllabus. This is electrophilic substitution reaction, ESR you can say, and this we must take an aromatic ether here. So this oxygen has lone pair of electron, so this lone pair can be delocalized to form like this. This is negative charge, this is double bond OR positive with a lone pair. This can be again delocalized. This is ortho position to which electron negative charge is there. Okay, so this can be delocalized here again. So let me draw the next resonating structure here. This is our OR plus lone pair. Here it is double bond, and this will be negative charge. There is double bond again here. So again like this to the ortho position there will be excess of electrons. So in resonance there are excess of electrons on ortho and para position. Okay, so this OR is an ortho and para directing group. This is, I'm writing here ortho, this is ortho and para directing group in ESR towards an electrophile. Okay, so I'm taking anisole as the example. Benzene OCH3 is attached. This is anisole. So when anisole is reacted with Br2 in presence of FeBr3, this reagent is, let me write here, Br2 in presence of FeBr3. So the electrophile in this reaction will be our Br minus ion, Br plus. So this Br plus will be directed to ortho and para position by this OCH3. So we will have these products. This is anisole to ortho position. There will be bromine and para isomer OCH3 bromine like this. Okay, 4-bromoanisole. The name IUPAC nomenclature of this compound is 4-bromoanisole, and this is 2-bromoanisole, and 4-bromoanisole, the para isomer is our major product. Okay, now let me go to the next reaction. This is bromination or halogenation you can say. So anisole is in the second case, in the second type of reaction, this is nitration. nitration of anisole. When anisole is reacted with concentrated HNO3 in presence of concentrated H2SO4, this is concentrated HNO3. Okay, so the electrophile in this case would be our NO2 plus. So this NO2 plus will be directed to the ortho and para position. Let me write the measured product only, the para isomer. Okay, this would be our measured product. This would be our measured product. The third reaction is sulfonation, and in sulfonation anisole is reacted with SO3, which will be our electrophile, and in presence of concentrated H2SO4. So the product will be this one. Let me again write the measured product only. This is our OCH3, and the SO3H will be attached to the para position. So the IUPAC nomenclature of this compound is 1, 2, 3, 4. So 4-methoxy benzene sulfonic acid. Let me say again, 4-methoxy benzene sulfonic acid. Okay, now let us move to this next reaction. The next, let me rub some here. Okay, the next reaction is Friedel-Crafts alkylation. This is Friedel-Crafts alkylation. Okay, Friedel-Crafts alkylation. In Friedel-Crafts alkylation, in anisole, it is reacted with methyl chloride in presence of AlCl3. This can be any alkyl group. Okay, so here when these two are reacted, our electrophile that will be generated will be CH3 plus. So CH3 plus will be directed to its para, ortho and para position. So to form this, let me write the measured product only. So this is our measured product. So methyl can be attached to the ortho position also, and that would be our minor product. This is our Friedel-Crafts alkylation. So the last reaction is Friedel-Crafts acylation. Okay, the last reaction is Friedel-Crafts acylation. So anisole is reacted with acyl chloride, acetyl chloride, CH3COCl. Okay, CH3COCl in presence of AlCl3, and electrophile that would be generated in this case will be this CH3 C double bond O, and this carbonyl carbon atom will have a positive charge. This will be our electrophile that would be attached to ortho and para position of anisole. Okay, so let me write the product here. The product of this reaction is Friedel-Crafts acylation. Okay, so acyl group will be attached to the para. This would be our product. This will be our measured product, and this acyl group can be attached to the ortho position as also. So the IUPAC nomenclature of this compound is this whole group is called acetophenone, and this carbon has to be numbered as 1, 2, 3, 4. So IUPAC nomenclature of this compound is 4-methoxy. This is acetophenone, 4-methoxy acetophenone. Okay, these are some electrophilic substitution reactions of anisole or ether, you can say. So let me give you a question which you can answer in the comment section. When this anisole is reacted with, this is an example of Friedel-Crafts alkylation. Okay, CH3 CH2 CH2Cl in presence of AlCl3, what would be the measured product formed in this case? You can comment the answer in the comment section. Okay, let me complete this video here. I think you have gained some knowledge for your examination. and this is a revision type video. And if you like this video, please share this video to your friends who are preparing for their class 12 examination to 2024. And if you are new to the channel, please subscribe the channel. Thank you.